Panigrahi.
Stage yours. Thank you, Pallav. So I thanks the organizer to let me speak you, and more than that, I am more thankful that I am listening to all the lectures for last few days, and I have learnt a lot, and I have more than that, I have more questions before I came here, and that's what tells the success of a conference. But I will tell you, all the talks, most of the talks were device oriented. It was exciting. And what I am going to talk may not be more exciting. So from fourth gear, I will take you to first gear. And that is what I may disappoint you. But the good part is that I may not have exciting things. And after lunch, so I will help you to go to sleep also. So that may be the good part of my talk. Because something talk about evaporation and which all of us know for basic undergraduate degree. And then just taking a cavity and talk about it, definitely it doesn't sound very exciting. But I will tell you, that is something which it got interested by working in something related to many problems. So I will share my experience, hope it will be useful to you. And just to get it started, I will tell you, that evaporation is taking place in many systems. I am showing you here that we start from sessile droplet, hanging droplet, and then a well, and I am talking about this well today. And this has many applications starting from heat transfer, printing, and many microfluidic devices. So cell culture and microarray protein crystallization. And then as far as the convection is concerned, that we see the convection inside the liquid, and we also see the convection or the vapor phase transport outside the liquid. So this is what is the domain we look into the convection in a microfluidic system. And then, before I start talking about it and then why it motivated this work, so I try to tell you that some of them is related to the heat transfer in a structured surface. I present you, just a paper in 2008. In this paper, they have used the structured surface for heat transfer, and then as you will be visible to you, there are a lot of structures, different kind of pitch, different kind of geometry, and including the plane heat transfer. And while you read the paper, you find out that they showed that sometimes it is good and structured surface is good for heat transfer. At some heat flux, it is not good. And these authors, they could say sometimes that why it is good, and sometimes they had no explanation that why it is not good. They left it to that future study. And that's what I saying that many times. We had some question now here. So then the next one, I tell you that this one is a paper in 2019 where there are two droplets, and then what it was showing that with time, the droplets were moving close to each other and they were merging. And the explanation by the authors that the vapor concentration between the droplets was changing with time when the evaporation was taking place. And they said that the disjoint pressure here gets affected by the vapor pressure. Vapor concentration, and that's what is leading to this, and that's what was their conjecture. Then the third application I was looking at it, here this is a microarray for screening the drugs, and that is what they had made 96 number of microarray to screen different kind of cancer drugs. And then you see in these drugs, what you see, that it is very, very important that the convection in the well is maintained at a uniform level. Otherwise, the concentration of the analyte, if it changed, then when in a 24-hour period, then the quality of the drug screening will not be proper. So there should be a controlled evaporation among all the wells there. And what they found out that the evaporation from all the wells are not same. and then that is what looks into it affect the performance of the micro well now. And they had no idea that why they cannot control it properly. Then I will tell you one of our study earlier, we were looking into the convection. So this one is a droplet in a single droplet. We did the micro PIV study, and you see the recirculation bubbles, where are two recirculation bubbles we saw. And then again we did between two droplets, and then you see rather than two recirculation bubble, and then we get one recirculation bubble. And then we tried to change this distance between that, and then what happened, you see the flow pattern inside the droplet was changing, and we at that time tried to understand what it was happening. And then I will tell you that one way we thought that a lot of things are happening, but we suspected that something vapor this vapor concentration here is affecting. So we came and could not do the measurements of vapor between that, and we tried to use the numerical simulation. And when we try to do the numerical simulation, and again you get tired doing the experiment, so we went to a simple route, and then we used the diffusion limited assumption, and we did the simulation here, and we tried to got the vapor cloud distribution around it, and we were successful to explain to many extent the results between the interaction between the two droplets. But the measurement is something which we have not done it there. And then I will tell you at some time we were doing the generation of protein crystal inside the droplet. And always you have one droplet, you will generate the protein crystal. We wanted to have many protein crystal developed, and similarly they were trying to do the parallel screening. We tried to put more number of droplets to have more protein crystal generation. And at that time, when we tried to do that, we saw the non-uniformity in the protein crystals from different droplets. And we had no idea why we are not able to get it. And we thought that it is an experimental uncertainty, and we left it there, saying that we could not do a good job when we are having a multiple droplet configuration. And saying this, then I will tell you that we now look into that there are multiple wells, there are practical applications, and convection is important. And from my experience, then we started asking a question that can we predict the evaporation rate from well cavity? And in fact, when we looked into the literature, you will find out most of the studies have been done for droplets. But when you go to cavity, there is nothing was available as far as the evaporation rate from the well. So we saw that it is not available. Then the next thing is there, if we want to model the vapor cloud behavior, which we try to use the diffusion assumption, is it really true or not? So we tried to give some explanation, had nothing to verify it. Then many of the devices, they had a heating for controlling the evaporation. So next is that, does the heating affect the vapor cloud behavior? So we were not having that information. And then the next thing is that as I was trying to increase the output of my protein crystal system, same as the drug screening, is the evaporation rate, I have more number of droplets, more number of wells, can I linearly multiply it and say that this is what is my total evaporation rate? Is it possible or not? And then how does the vapor cloud interact? That's what we have seen it, but then how does it really happen? So we are not sure about it. And with this question that I would like to say that I wanted to show these kind of answer these questions, that the vapor phase transport and evaporation from a well cavity, and when we heat it, how does it affect? And then when two cavities are close to each other, how do they interact with each other? So all these questions are around this what I am going to show, and definitely they will be related to some of the practical application. That's what is my objective. So when we start to doing the evaporation rate measurements, the first question came, that how do I measure it now? Or how do I now find out the concentration distribution? So we resort to holographic interferometry, and this is the arrangement that I have told you, shown you here, laser and the optics here, and this was the camera, and this is where I was putting the well, and then imaging in off-axis arrangement, and that's what you see, optical table, we put the droplet here, laser beam goes here, and the vapor cloud this is where we now get the vapor cloud laser beam interaction with it, and we record it in the camera. And then once we record it here now, and then the vapor cloud is changing in a three-dimensional manner here, and we get a two-dimensional measurements, and that's what I am trying to show. This is what is the intensity distribution in this plane, and we try to reconstruct it so that we get a three-dimensional distribution of the vapor cloud above the well now. And then, after we have this one, then how did we do the calculation? That path is what I am trying to cite it here. And you start taking the reference hologram, object hologram, and do the Fourier transform profilometry, get the phase and get the raft phase difference. And this is something which we have been doing it for many years. And then this is what, whatever phase difference you get, and that one is raft, and then you have to now unwrap the phase difference, and this is what, to develop the algorithm. There are many different algorithms which are available, like least square method, Ito method, and there are other methods, and we did not know what to use. Kept on looking into all the algorithms, both with simulated data and experimental data, and then found out the Goldstein algorithm is working the best, and we tried to use it. And once we try to get the unwrapped phase difference, then we have to reconstruct it, and we try to use the Abel transform, and then near the contact angle it was now diverging, and then what we try to use, we try to modify it using the Fourier-Hankel algorithm to find out the three-dimensional distribution of the refractive index. And then we use the Lorentz equation to find out the vapor mole fraction distribution in the vapor cloud. So what is the step? I am just showing it. This is the object hologram, this is the reference hologram, Fourier transform, and this is the wrapped phase, and this is the unwrapped phase. And then, this is how it look like, the unwrapped phase in the XY plane, and after reconstruction, this is how it look like the vapor cloud at this one. So after we try to get the vapor cloud distribution, then we have to find out the local evaporation rate, and the local evaporation rate, we try to get it from the concentration gradient from the holography, and from the concentration gradient, this is how we can calculate the local evaporation flux. And once you have the local evaporation flux, you can integrate it and find out the total evaporation happening from the cavity now. So considering that now we have the local evaporation flux and mole fraction distribution, and we also have the total one, all the time so many complex steps are happening, and you always wonder that are you doing a correct thing or not, or there is a mistake in experiment or mistake in your data analysis. So then, just to evaluate ourselves, and we try to do the gravimetric measurement of evaporation rate in a electronic balance of high precision. This is where we put the well cavity and then look into the change in mass from this balance with respect to time. And this is how with evaporation it was changing. And then we try to use from 90% to 50% and do the linear feed and to use it as a calculation of the evaporation rate. And then once we get this one, we know that we have the holographic data for this one. And then we calculate, take two fluid here. This one gives you the evaporation rate from the holography, and this gives the evaporation rate from gravimetry. And you see this one is 0.0210, this is 0.0215. And similarly for ethanol, you see that we could really get it very close to it, saying that the optical technique has been implemented correctly, and then we have confidence in our data and we can use it to move it further now. And now I will tell you that the original idea was to see the evaporation from the cavity, and we kept on, we are looking forward to come up with an expression which can be used to find out the evaporation from the cavity. So we did this, okay. So we did this for many different sizes of the cavity just to get a generalized trend of the evaporation. And then we try to use number of fluids here. And I have put the data here. They are vapor pressure, molecular weight, diffusivity, density ratio. And then as I am now trying to look into the evaporation process, so this one is now calculating the Grasshopp's number. And this Grasshopp's number for different size of the cavity, different fluid, these are the ranges which are given to here. Then we had the working fluid, and then these are various sizes of the cavity. And then again I had one question, can you use this for diffusion limited assumption, what we have been using, many authors are using. So we also did some simulation again for those experiments by using your Laplace equations, and then using this boundary condition, and then the COMSOL simulation to get it that what do we get when we use this assumption. And now this is the experimental sample experimental data. The first one is for pentane and hexane, cyclohexane and heptane. So you see that more number of fringes are with pentane, and pentane has highest volatility, and that's what you see that you have more number of fringes here now because you have more vapor now in this cloud now. And heptane has least volatility. You see the number of fringes are less here, and then the gap is also more here now. And then one more thing that you will see that this with time, I mean that the fringes you will see that evaporation is going to take place. The nature of that one is just almost similar, and finally the fringes disappear as your evaporation is complete now. So now you have the data now, and then we have the simulation from the diffusion limited modeling, which you see it in the right hand side, and left hand side is the experimental data for different fluids you see now. And then you can see now the vapor cloud. Look into this one here. This is what is the vapor cloud for pentane, and this is what we get it from simulation. Quickly you see the vapor cloud, they don't look is same now here. And then you can see it for all the fluids, that the vapor cloud is not same. Experiment is showing that it is like a flat shaped, and the simulation is trying to say that it is something like your spherical shape here. So giving question about the assumption which I was using, also many people we are using now. So then the next question is that we will try to see that the evaporation flux, we are getting it above the cloud. And now this one is the center of the cavity. This one is where the evaporation flux is maximum. And then you see that with different fluid, the evaporation flux above the cavity is different now. It depends on your fluid here now. And pentane has the highest amount of evaporation flux. And then once you get the local one, we integrate it here. And this one gives you the total evaporation rate with respect to the size of the cavity. And pentane, you can see the evaporation is increasing with the size of the cavity. And same thing for all of them. And that's what is also being explained from the cavity size now. And then you try to look into the process, we see that your total evaporation rate, we have it. We have now simulation data based on diffusion, and then based on total, we get it from your holography. And this is what you have a comparison that you see here. See, the total evaporation comes because of a contribution from diffusion and convection now. And what we did, we tried to get the diffusion part from this simulation here, and from the total we try to subtract it, and we say that any difference between the experiment and the simulation is because of the convection playing a role here. And here you see that this one is the diffusion one, and this one is the convection one. And for pentane, when you are increasing the diameter, and this is where the difference between your convection component is increasing. And physically it makes sense, you know, you have more diameter, Grasshopp's number is higher, and convection effect should be predominant, and that's what you see it, what your measurement is showing now. But when you go into heptane, you know that you have to remember the scale here is 1.6, here it is 0.15. So slightly blown up is happening here, but this is less volatile, but again, that's why you know less effect of convection, but then it is increasing with your radius of the cavity. So now we have a lot of data, and we now see that what convection is playing a role. We know the total evaporation rate. The next question is that can we now put them all together and come up with an expression which will give you the convection from a cavity now, which is not there. So as usual, we have the data. We wanted to see how does our data compare with the sessile droplets. And this is what we try to do. So looked into the correlation which is available in for the sessile droplets. So this is what we started using it here for all the fluids. And the difference that we saw is extremely large what we get it from a sessile droplets. And then, you know, it is slightly frustrating. We thought that at least we will prove that, you know, it is similar, and it was way off now. And then when I looked at this one, and I looked at it, what kind of correlation is this? It doesn't have a non-dimensional number. So fluid mechanics people, we don't like, you know, a correlation without non-dimensional numbers. So I did not like that correlation. I said that let us look into that and have a correlation based on the non-dimensional number. But when we looked for that, we found out these authors, they are also good enough. They have found out and they have come up with a next correlation which is based on the non-dimensional numbers here now. And then they have said that this is a better correlation for sessile droplet. So we say that now, okay, it is available, let us now use it here. And we now used it, and then what we see, that deviation from 400%, it came down to 100%. So it is correlation is better as expected, but still 100% something we cannot give it and saying that we had a correlation now. So we were not happy about it and thought that can we come up with a correlation which is more universal. And as you know that while looking into the data, then something kept on looking and just find out one thing, that there is some deviation here in positive side, some deviation here in the negative side. So negative side something is doing that something different for this heptane which is now trying to make it negative here. Can we come, you know, what is the difference between the two fluid, bring it into the correlation and come into with a modified correlation which will take care of this one. And this is what we try to think of, a correlation which will take care of that the difference between the working fluid. And what we did, we try to see that in this correlation, this is the developed correlation. So this density difference ratio, it usually takes care of the natural convection effect. Schmidt number takes care of the diffusion effect. And then we said that let us now, between that heptane and the other fluids, the most difference was the vapor pressure, and that's what is the volatility effect. And now we said that let us introduce a correction for this diffusivity correction factor, which is based on the difference in the vapor pressure. And this is what is the additional term which we try to introduce in the same correlation which was available. Just one more term with a power law here. And then we looked into the comparison, and then as you see that it came between from 100 to 10%, and then we could say that this is something which is now good enough to be used if we are going to calculate the evaporation from the cavities here. So that's what was the first objective that we have. And then the next one is that we had taken so much of effort to find out the concentration distribution in the vapor cloud, and I will just show you that here the concentration distribution in radial direction, we are plotting it here for pentane, and then this one is experimental one, and this one is from the diffusion limited calculation. This one is experimental and this is diffusion, and all of them are at two different heights. And now if you look into this, and what you will see that close to the interface of the liquid, that is Z equal to 1.5 mm, the diffusion and our experimental data, that calculation is having a better match. When you go away from that, then this is where the mismatch is coming into picture. So what it says, the convection effect is more as you go away from the interface, and diffusion is good enough when you are going close to it, and that's what is something also is physically what we expect it, and that's what we see it from here. And then again you know that in the normal direction, this one is your diffusion limited calculation, and this one is your concentration distribution in experiment, and it does show that there is a big difference also in the vapor cloud distribution from experiment on the diffusion limited calculation. And this one is a temporal characteristic, so I will just skip it, maybe you will have no time. So in summary of this part, what I have tried to put it here is that when you have a liquid well, and then this is how the evaporation is taking, highest evaporation takes, this is the evaporation one. If you have a diffusion limited calculation, it will look like this, your vapor cloud. And truly speaking, the vapor cloud will be something flattened. And this one is happening because you know it will come like this, and the vapor is heavier than the air. It will evaporate, come and go back like this, and that is why you have a flattened vapor cloud on top of that. So the next one is that you want to look into that effect of heating, and this is, you know, before you do that, we always know that heating can influence the behavior very much. Okay. So I will quickly now go and just show you know the message from this part and the other part. And so this one is what we said, and this one is thermal effect. And the way you see that the hydrocarbon vapor is heavier, and that's why it come down, that's what we see. If we heat it, then it become lighter, and the thermal convection effect will happen, so it will go in the other way. And then one is trying to bring down, and one is trying to bring up, so you are going to have a competing effect, and that's what we are expecting then when you are having a heated cavity. So we did the experiment for two fluids, and I will with a heated one. And then this one again, this, but more importantly, that I will tell that if we look into the heat transfer and mass problem, we see that Grasshopp's number will have two components. One is solutal and one is thermal component. So the Grasshopp's number now we divided into two parts and look into the solutal contribution and the thermal contribution, and then look into the evaporation of the vapor cloud. This is with temperature, and you see how the vapor cloud is happening for cyclohexane, and this one is for methane. And what you will see if you look into that, and you see that the behavior is different here now, that this one, if you look into the vapor cloud, this one is more in this manner, it is going more spherical, and this is more flattened. So what basically it is giving an indication that the solutal component Grasshopp's number and the thermal Grasshopp's number for two different fluid is different, and that is why the vapor cloud starts behaving differently. And we try to see, that the effect, I will see that this is the evaporation rate with respect to temperature, and we have compared the diffusion with the experiment, and Grasshopp's number for solutal and thermal, and come up with how they affect it here. But one message that we can see it here, that in this heavier hydrocarbon fluid, that we always think that as soon as you try to heat, the diffusion assumption will get violated more. That's what is the intuition here. But when we do and look at it, because even if you try to heat it, one of them is trying to bring this way, one of them is trying to bring it as well. Sometimes that for something it is not, diffusion is not matching here, and you see that this diffusion limited are good enough here, and as you go up, it is different, and depending on how the thermal and solutal is behaving, it is closeness to the diffusion limited are different now. So I will skip this one, and this whole idea is just to show the thermal and the solutal contribution and their effect, and at close to your low temperature limit for something, it is still good, diffusion is good, as you go away, it is not good. And this is 2 minutes I will take to do this one, because this one is about talking about the multiple interaction, how it is happening. So philosophically, I will tell that we have done, 2 droplets, we have seen it, we have done 4 droplets, I am not showing those data. There is marked difference here, but to have a complete influence on how this interaction is happening, so we came up with this, coaxial arrangement. We put the fluid here, and we took the fluid here now. And then now we try to look into the vapor cloud, which is coming here, and look into that. So the way we are trying to do it, that case 1, that we put fluid in one of them. Case 2, we put fluid in second cavity. Third one, we try to put fluid in both of them. So now, one we put it in one cavity, second we put it in second cavity, second one we try to put it in 2 cavity. And we had 2 arrangements in which this distance for one of them is 1 millimeter, another one is 0.5 millimeter. So we change the distance, and that is what we look into the evaporation rate and the flux. So I will not show these measurements, it is interesting, but the vapor cloud looks like that. But now, just one point that you see here, that just look into this one here. So case 1 is only one fluid here. Case 2 is fluid in the outside. Case 3, when both of them are here. Case 1, you look into the evaporation rate. This is from diffusion calculation, gravimetry measurement, and the holography measurements. So what it says, that this is fluid in 1, this is fluid in 2, this is fluid in both of them. So the evaporation rate in here should be this plus this. But what we see, that the evaporation rate is not this plus this. And that is what I am trying to see. If you have 2 fluids together, and you take one fluid separately and one fluid separately, the total evaporation rate is less than that. And that's give you an indication that how the interaction between these is now influencing your evaporation. And second one, you see that inner cavity, if you want to have together, because good thing about holography, you can now find out the local evaporation rate, and you can say how much this cavity is evaporating, how much this cavity is evaporating. So if you have a single one, how much evaporation will have? If you have look into the evaporation from the inner cavity, it is less than that. And then similarly, outer cavity, if you have 2 of them, and you look into a single of them, so it is less than that. So what point it is saying? That the evaporation rate, as you are having multiple one here, the evaporation from one is influencing the other, and this one is also influencing the other. The individual evaporation rate gets influenced here. So conclusion out of it here, all those evaporation well which we were saying, how do we arrange it, how do we are specifying it, they try to influence the evaporation rate from each other. The correlation that I have it now, I will say that I have correlation from one, measurement from one, I will have 100 well, I will multiply it with 100, so you will not get that one, you are going to get less of them, and it all depends on your arrangement. And again you see that same point is coming from the, just this is the one you see, only this one is here, see how much high evaporation, if they are together you know how this is less evaporation. That's what is coming from the evaporation rate. So you see that these are all distribution and showing the effect, I will conclude it here. So first one is quasi-steady evaporation result that from circular does not follow what we always use it. You have to use it with care, and correlation can be used. It is developed now, and the solutal convection is more dominating than the thermal convection in the temperature range which we have done it. And then you know this last conclusion is that the evaporation rate gets influenced when you have multiple cavities, they influence each other, which should be considered in designing multiple cavities. So thank you very much for listening.
Thank you, Professor Panigrahi, for the wonderful talk. Now there may be two small questions.
Yeah. Thank you for the interesting talk. What platform did you use to model the evaporation rate, and also what evaporation model was used?
Evaporation model for the simulation or for the experiment?
No, for the simulation.
Simulation, I just took the saturation pressure, such a saturation concentration at the interface of the well, liquid, and then take that as saturation concentration, and then outside ambient is ambient zero concentration.
Did you
and then use the Laplace equation.
Schrödinger's model or Lee model?
No. It is just to use the concentration distribution outside the liquid interface by using the Laplace equation. And then once we get the concentration distribution, then we used it to find out the evaporation.
Then how was the curvature model?
That one is just regular convection diffusion equation. So convection we took it out, regular diffusion equation. We solved it. So
no, but as the droplet evaporates, then the curvature
there was no model used
changes.
There was no model.
So as the droplet evaporates, the curvature changes, and then the evaporation rate changes as well.
Yeah. So this is what I am saying. This is just the equation that we used here. So this is your interface here, and this is the equation, and at the liquid air interface, the saturation concentration, and then away from it, it is C infinity. And then just solve the Laplace equation. And then once we solve it, and then from there we calculate the evaporation rate.
All right, thank you.
Thanks.
Yeah, okay, so I have a nasty question. He doesn't see me yet. Nasty question to methodology. So you use the Mach 10 interferometer, and then as always, you get the integral line of sight density differences, but you don't want that, so you use either tomography or you use the onion skin decomposition. But my question is, because then you get absolute density changes and you have to take the gradient, which is what you want.
Yeah.
So why didn't you go directly with a Schlieren that gives you gradient, and then a focusing Schlieren, and then you would have only the one two-dimensional plane.
Actually,
so a focusing Schlieren would be the natural thing I would do. And my question is, why didn't you do that?
Actually, my experience has said that that one will not be as accurate as this one.
Yeah. Okay, I agree. If it's working well, don't bother changing it. I agree.
No, that one is
I'm
simpler.
just curious to know.
Yeah, what you are saying, it is simpler than this one. We had to really struggle for that.
Yeah,
Actually, that one is simpler than this. But you know that usually, when we have a large gradient, then that's what the sensitivity is not good here. And here the sensitivity is so good,
It's much
you
better.
can never compare it. In such a small, because evaporation, how much gradient you are going to get it here, you may not be able to sense it there. And here you see that so much small change we can able to see it here.
Thanks.
Okay, so if there are no other questions, we'll thank Professor Panigrahi again.